Today we're doing a blower door test on this house to test how leaky it is, and from that we'll make our decisions on how to go forward building these houses again. So we start by putting a whopping big fan in the front of the house. We shut all the external windows and doors, open up all the internal doors, turn the fan on, and then we get a pressure difference between inside and outside. Okay, let's back up a bit and explain the air pressure difference between inside and outside. Basically what that does is enables us to test the leakage of the house. Now, we actually test the house at a range of pressures above and below 50 pascals, but 50 pascals is what we use to compare it to other houses tested at the same pressure. Now, the air pressure can be expressed in a few ways. One is ACH 50, which is air changes per hour, and the other one is permeability, which is measured in meters cubed per meter squared per hour. Now, this is what our Australian standards are set at. And our current standard maximum is 10 meters cubed per hour per meter squared. So the meter squared is basically the area of the walls, the floor and the ceiling. Due to the average proportion of our Australian homes, the air changes per hour figure is going to be pretty similar to the permeability figure. So if we end up at 5 air changes per hour, it's going to be pretty similar to 5 meters cubed per meter squared per hour. Anyway, that's the regulation stuff. So why is air leakage worth thinking about? There are a few reasons, but the one that will resonate with most people is money. So think of it like this. All the air inside your house in the winter is heated. So you're paying to heat that air. So the leakier the house is, the more money leaks out of the house. So all of that air that goes out of the house is replaced by air from outside the house. So the air from outside the house is cold and that comes in. So you have to heat that. Then that air warms up and then it leaks out. Then cold air comes in, you have to pay to heat it again. So what you end up doing is just continuously paying to heat outside air. And that's just money floating out of the house. Anyway, with that, we'll go back to site, follow through the house, and we'll check out where those leakage points are. Now follow me, we've got the blower door set up in the front door. What the blower door test does is basically test the air leakage of the house. This house was built probably 5 years ago. Our current standard is about 10 air changes per hour. So we'll have a look at the dial on this and just see how we're operating at 50 pascals. So as you can see, the door's running. We're about 49.9, 49.8, around the 50 air changes, the 50 pascals, and 11.6 for air changes per hour. Now, with our current standard being 10, this is below standard and very leaky. So we'll have a bit of a wander through the house and check where those leakage points are. It's worth pausing here to talk about what we're looking for, and it's worth taking one step back to mention our control layers. I'll talk about these control layers in another video, but for now, it's probably worth just mentioning what they are. We have 4 control layers. In order of importance, we have number 1, the water control layer, number 2, the air control layer, number 3, the vapor control layer, and number 4, the thermal control layer. Now, a blower door tests the integrity of the air control layer of the building envelope. So the building envelope is the line separating inside from outside, conditioned from unconditioned space, basically. So we're talking about the floor, the walls, and the ceiling. The air control layer for the walls in this house, which is typical for most of our Australian houses, is the internal plasterboard line. I'll put an image on the screen. This is not the house we're testing today, but it's a typical layout for teaching purposes. The building envelope is represented by the perimeter red line. Everything on the inside of the building envelope in yellow is inside. Everything outside of the building envelope is blue. So this is worth mentioning because it means that the roof space above the ceiling is outside and the attached garage is also outside. Our air control layer separates these spaces. Now back to what to look for. The blower door test will measure the leakage, but you need to know where to look. One way to easily understand or identify the weak points in the air control layer is to imagine filling the house with water and then imagining where that water is going to leak. A concrete slab is pretty safe, but a suspended timber floor is going to leak anywhere where there's a plumbing or electrical penetration through the floor or the bottom plates. Turn the house sideways and the water is going to leak through penetrations in places like behind the split system air conditioning unit, through windows and through electrical outlets. Now tip the house upside down and that water is going to leak through ceiling penetrations in places like where the sweep fan is, air conditioning grills and light fittings. So basically, if you think it's going to leak water, it's most certainly going to leak air. One of the main culprits with air leakage is a cavity sliding door. Now, with our handy piece of high-tech equipment, one ply toilet lever, we can see how leaky this door is. And down at the bottom. So basically we have air whistling through this. The worst part about this door, and this is a real no-no, it's a garage. Another main culprit for air leakage is exhaust fans. So this one's sort of like a tastic with a heat lamp in it. You'll notice the heat lamp themselves are actually connected to the roof space. So you have the air inside the room connected directly to the air inside the roof. Now this is really bad for energy because all the warm air that you're putting in here in the winter is basically going right up through your heat lamp. It's also bad for air quality because all of that air inside the roof, and you can imagine inside a roof all the bats and all the rubbish that gets on it, all that air is now connected to this airspace inside the house. So as far as air quality goes, what you end up breathing is air from the roof inside the house. It goes from the roof inside of the house, inside your nose, inside your lungs. We have another cavity sliding door connecting an ensuite to a bedroom, and quite a bit of air leakage through there as well. Another point of air leakage that we don't often think about and we think is pretty trivial are actually power points and any data entry through. You can see here, basically we've got wind whistling through. So what that means as well, just like before we had the air from the roof connected through the exhaust fan, in this wall we've got air connected through the wall, through the power point and inside the house. And again, that's air we're breathing, and it's also uncontrolled air. So as far as keeping air inside the house, leakage point, as far as keeping air from coming in from outside, it's just a really bad situation where it comes through and you're breathing air that you don't want to be breathing. Another part of air leakage is actually plumbing. Now, this house is on a timber floor. If you look at this basin, the basin's obviously plumbed somewhere. It's through the floor, and then underneath we're getting a whole heap of breeze coming through the cabinetry. So again, where's the air coming from? It's coming from under the floor into the house. What we really want to do with a high performance house is to contain the air. Once we contain the air, we can control the air. So if you're paying to heat or cool the air in the house, you want it to stay in the house. You don't want all that money that you've paid for going out through gaps and cracks and big holes. So the more we can do to cover those holes, to seal them up, the more chance we have of keeping that air inside. So all the money you've paid to heat or cool stays inside the house. Another point of air leakage is windows and sliding doors. Generally, glass sliding doors are a bit of a culprit for air leakage. Not the worst place of the house to have air leakage. But there's one little detail that most people don't think of. Now, quite often we talk about when we're building the house between the window frame, between the reveal and the wall frame, we put some low compression expanding foam or a mastic or something to seal that up. But the other thing is, between the actual aluminium frame and the window reveal, there can be a gap as well. So if you're going for a really high performance type of house, you can end up with leakage in this little point here. So if you gasket the fin of the glazing to the reveal, you can eliminate that leakage point as well. Here are two more potential leakage points. Recessed downlights in ceilings. The older style recessed downlights are shockers for air leakage. These newer ones are actually a little bit better. They're IC rated, IC standing for insulation contact. What that means is the insulation is allowed to go over the top of the downlight, so you don't have any gap in the insulation. Also, the IC rated downlights have a gasket to the ceiling, so they actually seal pretty well. But one existing point of weakness in most houses is the downlight, so it's really worth looking if you're doing an existing house as to what sort of downlights in there, and if you're building a new house, make sure it's an IC rated one with a good gasket. Also, split system air conditioners. This one's mounted towards an external wall. Basically, when it's mounted, there's a big hole through the plasterboard. Any hole like that really needs to be sealed up before you put the unit on. When we do a blow vortex, we often feel air just gushing down behind there. So we're just trying to cover up as many of those leakage points as possible. Another point of air leakage is cabinetry. Not the cabinetry itself really, but quite often what happens when you're building cabinetry or installing cabinetry, the plasterboard is often not behind it. So it's really better to sheet the whole wall with plasterboard and deal with that as your air barrier rather than rely on joinery. Because as soon as there's a gap, you're going to get leakage. And quite often there's air just gushing through from behind here. And remember, all of that air is coming from somewhere you don't want to breathe. Air from outside has dust, pollens, toxins in it. All that stuff comes inside. Most of the dust inside your house is coming from outside. So with a good air leakage strategy, you're going to prevent mice coming in, spiders, insects, mozzies, dust. You'll be good to go. Now I really want to highlight this door again. Remember, this is a cavity sliding door that separates the house from the garage. Now, when we're talking about air you don't want to breathe, imagine you've driven your car home, it's hot, it's sitting in the garage, you've got all this carbon monoxide in there, you go into the kitchen, which is right here, you turn your range hood on, and all of that air is being sucked in. You're breathing stuff you don't want to. And as far as cavity sliding doors go, you cannot seal them. So, never ever put a cavity sliding door between the house and the garage. If we zoom in here, you will just see a massive crack of daylight coming from the garage. So obviously with a massive crack right down there, right down the bottom, up the top, down the side, you cannot seal that. So just don't do it. Now we're having one last wander through the house with the fan turned up to about 85 pascals. Now there's a fair breeze coming through, so if we look again at our cavity sliding door, it's pretty bad. Just in general going through the house, we've got a lot of air. If you even look at the box here with the straps on it, there's a lot of air coming through. We'll wander through to the bathroom and you'll even hear the exhaust fan, which is not turned on, but you will hear it running. That's pretty bad. So what have we learnt from doing the blower door test on this house? The purpose of testing this house was to sort of see what our starting point was and to decide how to go forward building these identical houses again. We established that the house is pretty leaky, which is a problem. But on the upside, now we know where the leakage points are and we know what to do to make it better in the future. The biggest leakage point really identified was that cavity sliding door between the house and the garage. That's an easy fix. We just put a hinge door and seal it up properly. The other leakage points, which were the big ones, were the exhaust fans in the bathrooms. That's an easy fix as well. The cavity sliding doors on the internal of the house are another one, and also the power points and a few other things. But what we've really done is identified where these leakage points are, and we can quite easily put a strategy together. So we have a checklist along the way. When we build these houses again, we know exactly what to do. We know where the big holes are, we know where the small holes are, and we know what to do to fix it up. So going forward, with a decent strategy of air tightness, we can make these houses a lot better than it is now. Probably around the 5 air changes per hour is what we'll achieve, which is an excellent improvement over what it currently is. It will dramatically improve the energy efficiency of this house and also the indoor air quality and the comfort. So I think we can end up with a very good outcome just by doing some simple things to address the air tightness of this house. So that's it for the presentation. Thanks, everyone. Bye.